Hello, my name is Brianna Petit, and this is my extra credit project for Professor Schatz's Physics 1 class. I'll start out by working the paper calculations, which I've already worked out, and showing you how I did them, and then the VPython portion of the assignment. When I determined the speed of the jumper at the bottom of the swing, I used the energy principle up here, and as well as extrapolating it to this. Then I got the equations from there, plugged in the values, and got a V final of 27.8919 meters per second. I derived my K using Fgrav is equal to 1/2 Ks. For stretch, I used a chart given to me by a website called Physics for Cavers, which has a chart of different S values for different climbing materials used. And I used the one for the climbing rope that they would have used in this case. These are my calculations for part 2. I set tension equal to F air due to the reasons up there, and F air equals 1/2 CP AV squared. V I got from part 1. P was for Moab, Utah, which is 1.07. A I derived from the average male waistline and calculated the cross-sectional area, and then I got C from terminal velocity. For number 3, I set up a diagram up here using L1 is equal to 40.0465 meters because this is the initial length of the rope plus the stretch, and I used the tension force I just calculated. In addition, I again set F air equal to F tension and calculated F tension to be 0.2709 V squared. And then I plugged this into the value for F net, which I found using a table given in the book, mv squared over L2 equals ft minus mg. Solve this out to be V final equals 19.5007 meters. And from there, I used the equation I came up with up here, 0.2709 V squared equals ft, and ft was 103.0173 newtons. For number 4, I started with this chart given to me by a website called Physics for Cavers. It shows values for, this is the values that I used for a climbing rope. And I assumed that the load was equal to F grab plus F tension, added those up, changed it to pounds, and then used the chart to arrive at a stretch value, multiplied it by 130 feet for the initial one, and that yielded me a stretch of 0.3965, which validates our K from earlier because that was the K I used that was the stretch I actually used to find the K earlier, which my calculations in number 1 hinged upon. 5, I again started with the same chart and the same principle. The load, however, wound up to be considerably less, about 215 pounds compared to 240 pounds, which actually still corresponds to the same value of 0.01 for the stretch. Then I converted that over using a ratio of 215 to 240 for the two weights, and then I got that, multiplied it by the initial stretch, and this gave me a stretch of 0.009. Solved for L2, which is equal to 130 cosine 30 in feet, which is equal to 112.5833 feet. Multiply that by the 0.009 to get the foot stretch, and that became 1.013 feet stretch was equal to 0.309 meters. For number 1, on the VPython portion of this assignment, we're supposed to treat the rope as an ideal spring and predict the motion of the jumper. It's supposed to resemble the motion of the video. This is the VPython I used. Can't really tell much from it, I guess. Just let me hit play on it. And it should pop up a nice little animation, and here we go. Those arrows are showing the F grab, F net perpendicular, and F net parallel. For part 2, we're supposed to treat the rope as a spring and compute and display the perpendicular and parallel components of the net force of the jumper. As you can see down here, I've added print statements so that once it's finished running, it will calculate it. Let me hit play, and you can see it running it. The purple and the green are the parallel and perpendicular components of the net force. The yellow represents F grab. I wrote out my answers for number 3 and number 4 of the VPython section. The jumper is moving at the greatest speed at the very bottom of the pendulum, or rather of the arc of the pendulum, because as it goes up, it decelerates, and it accelerates as it goes back down. The same is true for the tension for the very same reason. This is the modified code for part 5, in which we were to change our computational model to describe the case of an ideal rope which has very little stretch. To do this, I lowered my spring constant significantly to around 10, and in addition, I changed the number of coils in the spring to just 1, made the thickness greater, and increased the radius of the spring. This produced this animation, which looks something like this, which moves a little bit slow. Here pretty much sums up my answer to number 6. All my predictions seem to be in line with computational ones. I hope that you enjoyed this video and that all my calculations made sense to you. Feel free to question any of them. I'm definitely not the best at physics. And have a good day, and thank you for voting for my video.